Right now, as you watch this, artificial intelligence is approving and rejecting mortgage applications. It is diagnosing cancer. It is deciding who gets bail and who doesn't. It is choosing which candidates get an interview and which ones get filtered out before a human ever reads their name. These are not science fiction scenarios. These are production systems, running today, at scale. So the question you should be asking is not, can AI do this? It demonstrably can. The question is, who is making sure it does it right? Who is making sure it is fair, transparent, secure, and accountable? That is the AI auditor, and that is what this certification is about. Welcome to the most comprehensive ISACA AAIA certification explainer ever made. Over the next several hours, we will walk through every single concept, every domain, every risk scenario, every audit technique, explained in plain language with visual animations that make the abstract concrete. The AAIA exam consists of 90 multiple-choice questions. You have 150 minutes to complete it. A scaled score of 450 out of 800 is required to pass. Domain 1, AI Governance, Risk Management and Compliance, carries 33% of the exam weight. Domain 2, AI Operations, Development and Lifecycle Controls, is the largest, at 46%. And Domain 3, AI Auditing Tools and Techniques, rounds out the final 21%. We will cover all three, completely. Let's begin. Domain 1 is the philosophical and structural heart of everything we will discuss. Before a single AI model is built, before a single data point is processed, governance must exist. Policy must exist. Accountability must be defined. Domain 1 asks the fundamental question: does your organization have the right structure, the right rules, and the right mindset to use AI responsibly? Everything starts with the machine itself. To audit AI, you must first understand what kind of AI you are looking at. There are 4 primary model types the AAIA exam tests you on. First, supervised learning. This is the most common type you will encounter in audit work. Imagine you are training a child to sort fruit. You show them an apple and say, "This is an apple." You show them an orange and say, "This is an orange." Over thousands of examples with correct labels, they learn the pattern. Supervised learning works exactly the same way. The model is trained on labeled data where the correct answer is already known, and it learns to make predictions on new, unseen inputs. Credit scoring, fraud detection, hiring tools, medical diagnosis systems. These are almost always supervised learning models. The audit focus? Training data quality and label fairness. If your labeled dataset reflects decades of discriminatory practice, the model learns discrimination. Garbage in, biased decisions out. Second, unsupervised learning. Here, the model gets no labels, no correct answers. It just looks at raw data and finds hidden patterns and groupings by itself, a process called clustering. The audit concern: unsupervised learning can inadvertently expose sensitive personal patterns or enable re-identification of individuals who were supposed to be anonymous. Third, reinforcement learning. Instead of learning from static data, an RL agent learns by doing. It interacts with an environment, takes actions, receives rewards for good outcomes, and gradually learns a strategy that maximizes total reward. But here is the audit nightmare. RL agents develop emergent behaviors. Behaviors that were never programmed, never anticipated, and sometimes never desired, but that technically maximize the reward function as written. An RL system told to maximize revenue might find loopholes that are technically profitable, but ethically catastrophic. Fourth, deep learning. Neural networks with many layers. The reason deep learning dominates image recognition, language translation, and medical imaging is that it can learn extraordinarily complex patterns that no human explicitly programmed. But this power comes with a profound audit challenge: the black box. The model might correctly diagnose cancer in an X-ray, but it cannot tell you why. The layers of mathematical transformations are too complex to interpret directly. In high-stakes decisions, medical diagnosis, credit approval, criminal justice, this is not just a technical inconvenience, it is a governance failure. You cannot hold a process accountable if you cannot explain it. You cannot appeal a decision you cannot understand. Effective AI governance rests on 7 core principles: accountability, clear documented responsibility for every AI system; transparency and explainability. Stakeholders must understand how AI makes decisions; fairness and non-discrimination. AI must not produce systematically unfair outcomes; robustness and reliability. It must work correctly under a wide range of conditions; privacy and security. The data powering AI must be protected; human oversight. Humans must retain the ability to review, challenge, and override AI decisions. And beneficial purpose. AI must be used for outcomes that genuinely benefit the people it serves. These are not aspirational platitudes. ISACA tests your ability to apply these principles to real scenarios where one or more is being violated. Governance without ownership is theater. At the top sits the AI Governance Committee, a cross-functional body setting strategy, policy, and ethical guidelines. The Chief AI Officer, or CAIO, owns the overall AI strategy. Data scientists build the models. Risk and compliance monitors AI-specific risks. Legal ensures regulatory compliance. And internal audit, U, provides independent assurance. One of the first governance controls an organization must establish before any AI is deployed to end users is the AI Acceptable Use Policy, the AUP. This defines what employees can and cannot do with AI tools. The ISACA exam mindset is clear. The AUP comes first. Before technical controls, before monitoring, before training, you establish the policy. Because without a policy, there is nothing to enforce. Risk management is where theory meets the real world. 6 categories of AI risk dominate the exam: algorithmic bias, lack of explainability, data privacy breaches, security vulnerabilities, model drift, and excessive AI agency. Every one of these carries critical severity. This is one of the most tested concepts in Domain 1. A model has a known bias rate that exceeds your organization's risk tolerance. What do you do? The naive answer is to deploy it and monitor closely. The ISACA answer, the correct answer, is to postpone deployment until the risk is managed within tolerance. You never deploy and hide and hope. AI risk cannot be managed in a silo. It must be integrated into the organization's broader enterprise risk management framework, sharing a common risk taxonomy, appearing in the central risk register, and reporting to the board alongside financial and operational risks. 6 data governance principles are critical for AI. Data quality: accurate, complete, timely. Data lineage and provenance: you must know where every piece of data came from. Data classification: without a policy, sensitive data is handled carelessly. Data privacy: GDPR, CCPA, and sector regulations impose strict requirements. Data retention: data must not be kept longer than needed. Ethical data use: the fact that data can be collected does not mean it should be. Scenario: a company trains a chatbot on customer records without sanitizing the data. A user asks an off-script question, and the chatbot reveals another customer's personal information. The greatest risk: disclosure of personal information. The best control: data sanitization before training. One of the most frequently tested scenarios: An employee exfiltrates organizational data by pasting it into an external generative AI tool. Greatest risk: unauthorized data disclosure. Primary control: CM monitoring of AI tool activity and a rigorous approval process. The EU AI Act is landmark legislation, the world's first comprehensive AI regulatory framework. It takes a risk-based approach, classifying AI systems into 4 tiers. At the top, unacceptable risk: AI that manipulates behavior, exploits vulnerabilities, or enables mass surveillance. These are banned outright. Below that, high risk: AI used in hiring, credit scoring, law enforcement, medical devices, critical infrastructure. These face stringent requirements: data quality controls, transparency obligations, mandatory human oversight, and conformity assessments before market entry. For the auditor, the EU AI Act's high-risk category is where your work matters most. Any organization operating high-risk AI in Europe must comply fully or face significant penalties. The NIST AI Risk Management Framework provides 4 core functions. Govern: establish governance structures, policies, and culture. Map: identify and characterize AI risks in your specific context. Measure: assess, analyze, and track those risks. Manage: prioritize, respond to, and recover. Together, they form a continuous cycle. ISO/IEC 42001 is the world's first international standard for an AI management system. Published in 2023, it mirrors ISO 27001 for information security and provides certifiable, auditable controls across all areas of AI governance. Critical exam differentiation: ISO 42001 equals certifiable standard. NIST AI. RMF equals voluntary guidance. OECD AI. Principles equals high-level ethics. Know which is which. The exam tests this distinction precisely. Organizations rarely build all their AI from scratch. They buy vendor models, license third-party data, integrate AI as a service platforms. Each relationship introduces third-party AI risk. When organizations purchase an off-the-shelf AI model, the most appropriate vendor management action is to establish clear contractual terms covering model update responsibilities, support obligations, performance SLAs, and liability for failures. Vendor accreditation alone is insufficient. When third-party licensed data is used in violation of usage restrictions, the correct action is immediate. Discontinue use of that data. Continued use creates legal and financial exposure. Stop first. Remediate second. Before we leave Domain 1, burn these 10 rules into your memory. They are the filter through which the AAIA exam asks you to evaluate every scenario. Rule 1. Ethics over efficiency. When a faster or cheaper option conflicts with an ethical one, ethics wins. Every time. Rule 2. Governance first. The first action in any governance failure is always to establish policy, not a technical fix. Rule 3. Prevention over correction. Proactive controls beat reactive ones. Rule 4. Root cause over symptom. Fix the source of the problem, not the surface. Rule 5. Human oversight over full automation. For high-stakes AI, human in the loop is always the preferred design. Rule 6. Data quality equals model quality. The training data is always the first thing to audit. Rule 7. Independence matters. Independent validation and segregation of duties are always preferred over self-assessment. Rule 8. Accountability equals governance success. Undefined ownership is the root cause of most governance failures. Rule 9. Postpone, don't compromise. If risk exceeds tolerance, halt deployment. Rule 10. Isolate first, notify second. Contain the breach before you communicate it. Welcome to Domain 2, AI Operations, Development, and Lifecycle Controls. At 46% of the entire AAIA examination, roughly 41 questions, this is not just the largest domain. It is the one that separates people who understand AI governance from people who understand how AI actually works. Domain 1 gave you the blueprint. Domain 2 makes you step onto the construction floor. You will need to know what happens when the data is dirty. What happens when the model drifts? What happens when an attacker poisons your training pipeline? We are going to move through 7 critical subdomains: data management, MLOps, change management, supervision, testing, threats, and incident response. Let's start at the very beginning. The data. Every single AI model you will ever audit begins in the exact same place: raw data. Before a model trains on a single data point, the organization must first perform exploratory data analysis, EDA. EDA is the act of getting to know your data, checking for null values, incorrect data types, duplicate records, and outliers that could corrupt the pipeline. But there is a more dangerous trap that lurks at the very beginning: data leakage. Think of a student who is shown the answer sheet before the exam. Their results look perfect, but they memorized the answers. They didn't learn. That is exactly what happens when an organization pre-processes and transforms their entire dataset before splitting it into training and testing sets. The rule is absolute. The train-test split must be the first operation performed on the dataset. Before normalization, before scaling, before feature engineering. If you see a scenario on the exam where a team processed data first and split later, flag it immediately as a data leakage risk. Imputing missing values with mean, median, or mode also carries a hidden risk. It distorts the true distribution of data, potentially masking important patterns and introducing subtle bias into the model. One of the most persistent data problems in machine learning is class imbalance. Imagine building a fraud detection system where 1 in 10,000 transactions is fraudulent. A model trained on this raw data will just predict not fraud for every transaction and boast 99.9% accuracy while completely failing at its actual job. To fix this, developers balance the dataset. Undersampling removes majority class records, but you throw away real data. Oversampling creates new minority class examples. The gold standard technique is SMOTE, Synthetic Minority Oversampling Technique. When an auditor identifies heavy class imbalance, the recommended control is oversampling through SMOTE, not undersampling. A dangerous encoding mistake. If you have ordinal data, data with natural ranking like economy, business, and first class, and you apply one hot encoding, you destroy that ranking entirely. The model has no idea that first class is higher than economy. Use ordinal encoding for ranked data. K-means clustering is extremely sensitive to 2 things: outliers and unit scale. A single extreme outlier can drag an entire cluster center away from where it belongs. Auditors must look for outlier handling and feature normalization documentation before any clustering model is approved. Where does an AI's data come from? Often from multiple external sources: user submissions, third-party databases, scraped web content. Each one of those channels is an attack surface. A data poisoning attack happens when an adversary deliberately injects corrupted or mislabeled data into the training pipeline. The model learns from poisoned material and develops a hidden bias or backdoor that the organization never detects until real-world harm has already occurred. The exam question presents a scenario like: a competitor submits fake product reviews influencing the AI's engine. Best control: authenticate your data sources before ingestion. Dataset version control is equally critical. Without it, when a model produces a biased or incorrect output, you cannot answer the most important audit question: What data trained this model? The model becomes unauditable and irreproducible, two fatal characteristics in any regulated environment. When organizations use synthetic data, they must validate it rigorously. A synthetic data set must be mathematically proven to accurately represent the statistical distribution of the real-world data it replaces. Low-fidelity synthetic data produces biased models that won't surface problems until deployment. Traditional software has a simple life story. If nothing in the codebase changes, the software doesn't change. AI does not have that luxury. An AI model trained on data from last year may be completely wrong today, not because anyone changed the code, but because the world changed around it. This is why traditional DevOps is insufficient for AI. We need MLOps. MLOps has 4 continuous pillars. Continuous integration. New code and data are automatically merged and tested. Continuous deployment. Validated models are safely released to production. Continuous training. The MLOps superpower that DevOps doesn't have. The system automatically detects when data distribution shifts and triggers retraining. Continuous monitoring. Performance, fairness, and stability are tracked around the clock. If an organization lacks a formal MLOps framework, they are operating AI without a safety net. No reproducibility. No automated quality gates. No performance visibility. That is a significant audit finding across all 4 missing pillars. The AI Lifecycle flows through 6 stages: design, development, training, deployment, monitoring, and maintenance. An auditor must verify that appropriate controls exist at every single stage. During the training phase, the most common failure mode is overfitting. A model memorizes the training data so precisely that it traces every quirk and anomaly of that specific dataset. It performs perfectly in the lab, but fails in the real world because it never learned generalizable patterns. It memorized the answers. The best mitigation is cross-validation, testing the model across multiple different subsets of data during training. For deep learning specifically, neural networks learn through backpropagation, a mathematical technique that calculates errors at the output and works backwards through the network adjusting weights. Here is the hidden danger. If biases exist in the training data, backpropagation amplifies them. Layer by layer, the bias signal grows stronger. Without active controls, a deep learning system trained on historically biased data becomes a powerful, precise engine of discrimination. Before any model enters production, the greatest audit concern is the absence of external validation, independent testing by a team that had no part in building the model. If the builders are also the validators, you have a conflict of interest. Critical incident scenario. An unauthorized model replacement is discovered in production. The immediate first action is to revert to the last verified, authorized model. Secure the system first. Root cause analysis comes after. In traditional IT, a change means a code update. In AI, change management operates in 3 dimensions simultaneously: code changes, data changes, and model changes. All 3 are interconnected. A change in one can cascade to the others in ways that traditional change management processes completely miss. A scenario the exam loves. It applies a standard security patch to the underlying AI inference engine. Standard IT change management says approved, compliant. But the auditor's first priority is to investigate the patch's effect on the model's performance. A patch can subtly alter floating point calculations or modify library dependencies, changing predictions without touching a single line of model code. Golden rule. Every model retraining event is a formal change. Even if the algorithm is identical and only new data was fed in, the resulting model is different. It must go through a formal impact assessment covering 4 dimensions: performance impact, bias and fairness impact, security impact, and compliance impact. Once deployed, every AI model begins to age, not because its code degrades, but because the world keeps changing while the model stays frozen in the past. This degradation is called drift, and you must know the difference between two distinct types. Data drift happens when the statistical distribution of real-world inputs changes over time. The model was trained on data that looked like X, but now incoming data looks like Y. Concept drift is more fundamental. The real-world relationship between inputs and the correct output actually changes. A fraud detection AI, trained before a major economic crisis, may flag behaviors as suspicious that are now entirely normal. Concept drift requires ground truth monitoring to detect. Perfect exam scenario: a retail inventory. Trained in September, fails completely to predict the holiday shopping surge in November. That is classic concept drift. The buying relationship between products and seasons changed dramatically. Correct mitigation: continuous monitoring plus automated retraining. Auditors measure drift using the Population Stability Index, PSI. 0 to 0.1 is stable. 0.1 to 0.2 is moderate drift. Monitor carefully. Above 0.2 is a critical alert requiring immediate review and likely retraining. Traditional software is deterministic. Same input, same output, every time. Generative AI breaks this rule entirely. Gen AI is probabilistic. A large language model processing the identical prompt at two different moments can produce two completely different responses. This creates a profound audit challenge. How do you establish accountability for an AI that never behaves exactly the same way twice? The answer lies in audit trail architecture. For generative AI systems, the audit trail must capture the exact input submitted and the exact output generated at the time of execution. Not just a log entry saying the AI responded. The specific response. This is the only way to reconstruct what happened in any dispute. For high-stakes AI decisions, loan approvals, medical diagnosis, legal analysis, human-in-the-loop oversight is mandatory. The AI proposes. The human decides. If a credit-scoring AI is generating sudden, unexplained score changes, the best long-term mitigation is periodic human expert review and calibration. When a fraud detection AI generates too many false positives, flagging legitimate customer transactions as suspicious, the most likely root cause is unoptimized hyperparameters. The model's decision threshold has been set too aggressively. Hyperparameter tuning is the targeted fix. Precision answers. Of all the times the model raised an alarm, how often was it correct? Recall answers a different, more critical question. Of all the actual positive cases that existed, how many did the model successfully find? For safety-critical systems, cancer detection, structural failure prediction, autonomous vehicle hazard recognition, the primary metric is always recall. Missing a real threat is catastrophic. Now, testing for bias. Organizations must apply the 4/5 rule. If the approval rate for a protected demographic group is less than 80% of the approval rate for the most privileged group, the AI is discriminating in a legally actionable way. The demographic parity ratio below 0.8 flags potential bias. The disparate impact ratio below 80% triggers a potential regulatory violation. The single greatest audit concern before any model enters production is the absence of an independent validation team, a group with no involvement in the model's creation. When the developers validate their own work, you have an inherent conflict of interest and no independent quality assurance. This is not just bad practice, it is a governance failure. When evaluating large language models for enterprise deployment, the temperature parameter must be audited. Temperature controls how creative or random the AI is allowed to be. A high temperature increases hallucinations, the AI generating confident, fluent, completely fabricated information. For factual enterprise applications, lowering the temperature is the best control for reliability. To stress test model resilience, organizations should conduct AI red teaming. The primary objective of an AI red team is not to find software bugs. It is to identify weaknesses in the model's ability to resist adversarial inputs, specifically crafted to trick, manipulate, or destabilize its predictions. Pure random testing is dead. If a facial recognition model achieves 99% overall accuracy but fails 80% of the time for one specific demographic group, a random sample would likely miss it. Stratified subgroup testing divides the test population into demographic categories and tests each group independently, making hidden performance gaps impossible to miss. Subdomain F. We are on the battlefield. There are 4 fundamental adversarial attacks every AI auditor must know by name, mechanism, and control. First, the evasion attack. This targets a deployed model. The attacker applies subtle, mathematically calculated perturbations to real-world inputs, changes invisible to humans but large enough to push an input across the model's decision boundary. A stop sign with specific tape becomes a speed limit sign to an autonomous vehicle's AI. Defense, adversarial training plus strict input validation. Second, the poisoning attack. At training time, malicious data is injected into the pipeline. Best control, authenticate data sources. Third, model inversion. The attacker queries the deployed model to mathematically reconstruct sensitive records from the training data. Control, differential privacy during training. Fourth, model extraction. A competitor systematically queries your production model, records input-output pairs, and trains a near-identical clone. They steal not the model file, but its learned behavior. Mitigate with API rate limiting, query anomaly detection, output watermarking, and query restriction policies. Generative AI introduces prompt injection. A malicious actor crafts input text designed to override the AI's system instructions, causing the LLM to disclose private information, reveal system configurations, or execute unauthorized commands. Defense requires multiple layers: input validation, output monitoring, and CM integration to correlate activity logs. Attackers also use jailbreaking, convincing the AI to abandon its ethical guardrails. The most effective technique is presenting the AI with hypothetical, fictional, or role-playing scenarios. When the request is framed as you are acting as a character in a story, with no restrictions, the AI's ethical filters struggle to apply policy to apparently fictional content. If an AI system's model configuration, architecture details, hyperparameter settings, is leaked externally, the most significant risk is that attackers can craft perfectly targeted exploits based on the exact known weaknesses of that specific model. The ultimate exam scenario: a confirmed AI security breach is actively occurring. What is your very first action? Contain first. Isolate the impacted AI systems immediately. Only after the system is isolated do you investigate. Only after you understand what happened do you notify stakeholders. A standard IT incident response plan is completely inadequate for AI. An AI incident can be an invisible slow-motion failure unfolding over weeks or months. A poisoned model might operate for 6 months before producing a detectable pattern of wrong decisions. An AI-specific incident response plan must explicitly include protocols for model drift response and data integrity attacks, 2 categories that standard IT plans completely omit. When investigating an AI incident, traditional forensics is insufficient. AI forensics requires 3 pillars working simultaneously. Data. Forensics: analyzing training data, input streams, and the data pipeline for corruption. Model forensics: examining the model's internal parameters and weights to understand how its behavior was altered. Log analysis: reviewing all system telemetry to reconstruct the timeline of events. Speed is a governance obligation. The mean time to contain, MTTC, measures how quickly a confirmed AI incident is isolated and stopped. For a critical AI system, an MTTC exceeding 1 hour is a critical gap. AI systems can make thousands of wrong decisions per hour. Every minute of delay compounds the harm. AI disruption scenarios must be embedded in the organization's enterprise disaster recovery plan. If the DR plan only addresses server failures and network outages, it is not prepared for AI-specific failure modes. Congratulations! You have navigated the most technically demanding domain in the AAIA curriculum. Domain 2 was the engine room. Domain 3 is the control room. Domain 3, AI Auditing Tools and Techniques. 21% of the exam, 19 questions, and every single one tests a specific skill: your ability to actually conduct an AI audit. Domain 3 requires you to bring classical ISACA auditing discipline, professional skepticism, independence, risk-based planning, evidence sufficiency, and apply it to a world that traditional audit methodology was never designed for. Machine learning pipelines, stochastic model outputs, adversarial attack surfaces. 5 subdomains. Let's plan the audit. Every audit begins with a plan, and in AI auditing, the quality of your plan determines the quality of your assurance. ISACA mandates a risk-based approach. The highest risk systems, AI making healthcare diagnoses, approving or denying financial credit, powering autonomous vehicles, receive the deepest scrutiny and the most experienced audit resources. A mature AI audit follows a phased approach. Phase 1 evaluates governance. Are the right policies, accountabilities, and oversight committees in place? Phase 2 evaluates operational controls. Is MLOps functioning? Is change management working? Phase 3 gets hands-on with model testing, bias metrics, fairness data, explainability tools, and adversarial resilience. The audit scope document must explicitly define the system boundaries, which AI components are in scope, the lifecycle stages being reviewed, the organizational units involved, and the specific time period the audit covers. When using AI tools to assist in audit planning, the greatest risk is feeding the tool incomplete or low-quality data about the organization's AI environment. Incomplete inputs produce a flawed risk assessment, and your entire audit is built on a faulty foundation. Traditional audit sampling is random, but in AI auditing, it can completely fail you. If a loan approval AI has a subtle bias against a group representing 3% of applicants, a random sample might include only 6 or 7 cases from that group, statistically insufficient to detect the pattern. Stratified sampling a demographic group is the solution. Deliberately oversample minority groups so each demographic stratum is independently testable. For AI systems operating at machine speed, high-frequency trading, real-time fraud detection, point-in-time audits are fundamentally inadequate. These systems require continuous auditing, technically implemented through embedded audit modules built directly into the AI pipeline, evaluating every decision against predefined criteria in real time. When auditing the training stage, your primary focus is data fairness, not model accuracy. Biased training data guarantees a biased model regardless of how accurately it classifies the training set. Know your metrics. For a natural language processing model, text summarization or translation, the correct reliability KPI is the Rouge score, recall-oriented understudy for gisting evaluation, not the ROC curve, not mean squared error. Rouge measures how much of the reference summary's language the AI successfully captured. AI systems generate enormous volumes of performance data. Organizations are often eager to share dashboards and accuracy reports with auditors. And herein lies the trap. An auditor who accepts client-provided performance metrics at face value without independently extracting and verifying the data, has fundamentally compromised their independence. Professional skepticism in AI auditing means you pull the logs yourself. You run your own queries against the production data. You apply your own fairness calculations against the actual transaction records. This principle extends to who validates the model before deployment. Self-assessment by the development team, the same people who built the model, is an inherent conflict of interest. An independent validation team with no stake in the model's approval is a critical control. When that independence is absent, the AAIA exam answer is clear. It is the greatest concern before production deployment. For AI systems integrated with web applications, the most important security control from an audit evidence perspective is CM integration. A security information and event management system aggregates logs from all components of the AI environment, enabling detection of complex multi-vector attacks. Without CM, you have blind spots an attacker can exploit indefinitely. To prove that training data and model files have not been tampered with, auditors use cryptographic hashing. A hash function takes a file and produces a unique fixed-length fingerprint. If even a single bit of the file changes, the hash changes completely. By recording the hash at a specific point in time and verifying it hasn't changed, auditors establish an unbroken chain of custody. A critical requirement for audit evidence reliability is reproducibility. If a client claims their model achieves 95% accuracy, the auditor must be able to independently reproduce that result using the documented training configuration and data version. If the result cannot be reproduced, the evidence is unreliable. For large multi-source AI datasets where different tables reference each other, the best method for validating completeness and consistency is referential integrity checking. And if you use generative AI to help write audit reports, the greatest risk is that the AI subtly alters the intended meaning of your findings. Before you can draw any conclusions from data, you must assess the quality of that data across 5 dimensions. Relevance. Is the data measuring what matters for this objective? Accuracy. Is it free from errors? Completeness. Are records missing that would change the conclusion? Timeliness. Does it reflect the current state? Consistency. Does it align across different sources and time periods? Flawed audit data produces flawed conclusions regardless of how rigorous your methodology is. For diagnostic analytics, understanding why something failed, auditors use explainable AI tools, LIME and SHAP. SHAP assigns each input feature a contribution value for a specific model decision, showing exactly how much each variable pushed the output in a particular direction. LIME creates a simplified local approximation of the complex model around a single prediction, making it interpretable to a human reviewer. Together, LIME and SHAP are your X-ray machines for the black box. When a model makes a discriminatory or incorrect decision, these tools tell you precisely which data features caused it. Predictive analytics looks forward. Rather than explaining past failures, it uses trend data to anticipate future model drift and performance degradation before they materialize. This shifts the audit from reactive to preventive, the ISACA gold standard. For data governance audits, the most important thing to evaluate is accountability. Clear data ownership is the strongest predictor of governance maturity. Every ISACA audit finding must contain 4 mandatory components: the condition, what the auditor observed; the criteria, the standard, policy, or control objective against which the observation is being measured; the cause, the root reason the gap between condition and criteria exists; the effect, the actual business, financial, regulatory, or ethical impact of the finding. Without all 4, the finding is incomplete. A report that states the model lacks version control without explaining the business effect gives management no compelling reason to act. Communication must be tailored to the audience. Engineers and data scientists receive precise technical language, specific parameter names, metric thresholds, architectural vulnerabilities. Senior executives and the board receive business impact, financial exposure, regulatory risk, and reputational consequences. The same finding, two completely different presentations. A critical ISACA principle that many candidates miss. The audit is not complete when the report is issued. It is not complete when management agrees to remediation actions. The audit is only complete when the auditor has independently verified that the agreed remediation actions have been implemented and confirmed as effective. The most serious risk in AI auditing: false assurance. If an audit team conducts an AI audit without possessing the specific expertise required, without understanding MLOps, Explainable AI, adversarial threat vectors, or AI ethics, they produce a report that appears thorough while missing the most significant risks. The board believes they have assurance. They do not. Minimum credential expectations include ISACA, AAIA, or CISA, with demonstrated AI specialization. We now reach the Master Metrics reference, every quantitative KPI and KRI the AAIA exam tests. Pause here and screenshot these tables. Performance and quality metrics first. Accuracy measures the percentage of correct predictions, reliable only on balanced datasets. Precision minimizes false positives, ideal for spam filters. Recall minimizes missed threats, making it non-negotiable for safety-critical systems. F1 score is the harmonic mean of both. Use it when the dataset is imbalanced and both dimensions matter. AUCROC measures classifier separation ability. For natural language processing, use the Rouge score. For regression models predicting continuous numbers, use mean squared error. Bias and fairness metrics next. Demographic parity checks that positive prediction rates are equal across groups. A ratio below 0.8 is a bias flag. Equalized odds verifies that both true positive and false positive rates are equal across groups. Disparate impact. Ratio below 80% triggers the 4/5 rule regulatory violation. Equal opportunity focuses on equalizing true positive rates specifically for underrepresented groups. Drift and stability metrics, your early warning system for model degradation. The Population Stability Index, PSI, is the most frequently tested metric. 0 to 0.1, stable. 0.1 to 0.2, monitor. Above 0.2, critical alert. Retrain. The KS statistic compares statistical distributions between training data and live production data. Above 0.1 indicates moderate drift. Model accuracy decay tracks the drop in predictive performance since deployment. A greater than 3% drop triggers retraining review. Concept drift. Score monitors the changing relationship between input features and target variables. Security and resilience metrics. Adversarial success rate measures what percentage of adversarial inputs successfully fool the model during red team testing. Above 5% indicates the model needs hardening. Data poisoning detection rate measures pipeline capability to catch malicious training data. Below 90% is a critical gap. False acceptance rate is critical in biometric systems. Any rate above 0 requires investigation. Mean time to contain for a critical AI breach. Above 1 hour is a critical incident response gap. Unauthorized change detection time. Above 24 hours is a critical monitoring failure. We have now journeyed through the full landscape of the ISACA AAIA certification. From the governance frameworks that establish the rules, to the operational controls that enforce them, to the auditing tools and techniques that verify they are working. The AAIA certification is not just a credential. It is a commitment. A commitment that as AI reshapes every dimension of human society, there will be professionals equipped to stand between powerful technology and the people it serves. Professionals who ask the hard questions, who verify, not trust, who protect the integrity of the systems that an increasingly digital world depends upon. You are now equipped with the knowledge that ISACA expects of their most advanced AI auditors. Pass your exam, and then go audit something important.